Hello, and thank you for attending my talk today on hierarchical cyber attack detection in large-scale interconnected systems. My name is Alexander Julian Gallo. I am from TU Delft, and I'm presenting here my work together with Twan Keijzer and Riccardo Ferrari. Let me start by providing a little bit of an overview of the motivation of this work. So modern control systems are characterized by pervasive automation, by distributed sensing and computation, and by reliance on communication networks. This has been possible due particularly to the reduction of costs both of microcontrollers and of communication devices. This has led to the definition of a new paradigm, the paradigm of cyber physical systems, where both the cyber and the physical part of control systems are considered explicitly. These cyber physical systems often describe safety critical systems, such as industrial controllers, industrial control systems, electricity distribution networks, or manufacturing plants. For these systems, failures have very severe consequences, both in terms of physical dangers to the users and operators, economic losses for the operators, as well as environmental damage for society as a whole. These sources of failure may be both faults or attacks, and it is the objective of controllers for these safety critical systems that they guarantee performance while limiting degradation caused by the failures. So in this paper, we are considering cyber attack detection, which is a reactive strategy towards cyber attacks. The presence of cyber attacks has been ushered in by the use of the communication network for closing the loop of the controllers, which on the one hand provides better information sharing and therefore more efficient control, but on the other also presents a significant vulnerability. Cyber attack detection is reactive, so it wants to detect attacks that are already present in the network, and it's not trying to robustify the communication network in any way. The diagnosis strategies that are implemented rely on secure information, such as knowledge of the fact that the physical dynamics will not change, because attackers do not have access to them if they are cyber and they're in the communication network. Prior model knowledge of the system that may be possessed by the operators, as well as the comparison to measurements in order to make these decisions online. Okay, having presented the problem, let me set up having presented our objective, let me set up the problem. So we consider large-scale interconnected systems in which the system as a whole is partitioned into physically coupled subsystems. The subsystem dynamics are defined as linear discrete time dynamics, in which there is a term, this DI, which represents the physical coupling between subsystems. We suppose that there is a hierarchical control scheme that is acting upon the large-scale system, in which local decentralized controllers provide stability for the large-scale system, as well as reference tracking. So asymptotically over time, without the presence of physical coupling, Xi will approach a transformed reference. So it will approach pi IRI. And in the presence of physical coupling, it will approach a neighborhood of the reference. The reference is defined and transmitted by a centralized supervisory controller, which transmits the reference, which defines the reference at every time instant, and then transmits it to the local controllers in order to perform coordination. In order to better design this reference, we suppose that there is a local coupling estimate, DIL hat, which is transmitted from the local controllers to the supervisory estimate. DIL hat is an estimate of the physical coupling between subsystems. So we suppose that there is a vulnerability and there is a cyber attack that is able to control a local controller. So it's able to take over a local controller. As such, it can inject signals into the actuators of the subsystem, so this delta UI, as well as altering the information that is being transmitted from the local controller to the supervisory controller. Its only limitation is that the supervisory controller cannot itself be compromised. The reason for this is because the supervisory controller is centralized, and as such, it poses a single point of failure risk, and therefore may be protected by some more sophisticated strategies to prevent the presence of attacks. The diagnosis scheme that we present in this paper is hierarchical. This means that it is reliant on the centralized supervisory controller taking information from the local controllers in order to detect the presence of an attack CIL. The methodology that we use is based off of the comparison of the physical coupling estimates. So on the one hand, it receives the local estimates from all the controllers for coordination purposes. And on the other hand, it is capable of designing its own supervisory estimate in order to compare it with what is being received from the local estimate, from the local controllers. The supervisory estimate is defined at the supervisory level, and it uses knowledge of the set points, so knowledge of the references RI, without any direct uses of the state dynamics, in order to compute an estimate of the physical coupling between subsystems. On the other hand, the local estimates use local measurements and knowledge of the subsystem dynamics, as well as an unknown input reconstruction strategy in order to design an estimate of the physical coupling between themselves and all of their neighbors. The diagnosis scheme that we design is set-based, and it is founded on the use of the uncertainty bounds of these estimates. So these estimates will not be exact due to lack of full information at any one node, and therefore there is an uncertainty within which they live, and this uncertainty set will be used for diagnosis. Okay, so having presented an overview of our scheme, let's delve into the specifics. So the first estimate that I'm going to present is that of the supervisor. The supervisory estimate DS hat relies on knowledge of the coupling matrix, this AC, which is the collection of all of the coupling matrices between subsystems, and as well as knowledge of the reference points that it sets for each subsystem. Given this definition, we can define an error bound. Indeed, DS hat is going to lie within a neighborhood of D, when this neighborhood is defined by ES. ES, the definition of ES is mildly technical, but it relies on conceptually, it relies on the fact that each state will asymptotically track the reference that is being given to it, given the design of the local controllers that are designed to be reference tracking. Therefore, the supervisory layer is able to construct an estimation set, this calligraphic DS, which is equal to the D of S, so to its own estimate plus the estimate error bound. This implies that without any attack, the coupling between subsystems lies within this set. The knowledge that is necessary in order to produce this set is threefold. It requires knowledge of the reference, which indeed is known to the supervisory controller as it is defining them itself. Knowledge of the coupling matrices, as well as knowledge of the local convergence rate, BI, so the convergence speed with which each subsystem tracks the reference. So this is quite limited subsystem information, and we believe that it is an acceptable amount of information for a supervisory controller to have about the local subsystem without needing the entire dynamics of each subsystem. On the other hand, the local estimate is based on a reduced unknown input observer. A reduced unknown input observer was presented in Lan and Patton in 2016, and it relies on an augmented state dynamics. So a dynamical equation in which the subsystem state is augmented with the coupling between subsystems. So DI is present in the dynamical equation, which can be written in compact form using the definition of XI bar, which is XI over DI. And then the reduced unknown input observer is filtering the local measurements, so it's filtering out measurements yi to give an estimate dil hat of the physical coupling. The design of the reduced unknown input observer is constrained by these matrix definitions, which I am not going to go into. The only thing that I will mention is that MI, so the dynamical transition matrix of the UIO state, is stable. Because it is stable, the estimation error is such that it asymptotically tracks, it asymptotically converges to the origin. If di bar, which is the difference between the physical coupling at different time instances, is zero. If the physical coupling at different time instances is different from zero, it will asymptotically track a neighborhood of the origin. It is therefore possible to define a bound on this error, and so it is possible to define this set, a calligraphic E of L, which has a dynamical evolution. The dynamic evolution is based off of the dynamics of the estimation error, as well as a bound on the one-step change in the physical coupling between subsystems. Because of its definition, the coupling, so D, is known it is known to lie within EL centered in the estimate DL hat. It's important to notice that the error set and the error set is computed at the supervisory level. This is necessary for us to be able to perform detection, as I will show in later slides. And therefore, the supervisory also needs to have knowledge of the matrices MI and TI, which are the matrices of the reduced unknown input observer. Okay, we can now, having defined all the pieces, we can now design our diagnosis strategy. So our diagnosis strategy, as I mentioned, is computed at supervisory level. And it uses an indirect way of testing and constructing the residual. It is the detection test, it is set-based, and the supervisory tests whether the intersection between the estimate set DS and the estimate set DL are intersecting. If they are not intersecting, then it's considered that an attack is detected. The reason why this detection test is sensible is that we know that the physical coupling between subsystems must lie both within DS and DL during nominal conditions. And therefore, in nominal conditions, there must be at least one point of intersection between these two sets. And so if there is no intersection, then there must be something wrong with the system. And in our case, there must be an attack. In order to represent these sets, we use constrained zonotopes. We use this because they are closed under addition, multiplication, and intersection, and they have good computational properties. Other set representations are also can also be adopted. It's just that in order for the scheme to work, they must be, and if they're not closed under these operations, their outer approximations must be introduced in order to perform all of the necessary operations. Okay, so this scheme has the following detection properties. First of all, it doesn't have any false alarms. This is by design. So the physical coupling between subsystems lies within DL and DS in nominal conditions, and therefore their intersection is non-zero if there is no attack. On the other hand, it is possible to define a set within which an attacker can remain the other way around. So we can define a set within which if the attacker is there, it is guaranteed to be detected by our diagnosis strategy. This is quite important when trying to analyze the performance of diagnosis strategy overall. The other characteristics of our scheme are the conditions under which the attacks are stealthy. So here we define both locally and globally stealthy attacks. And locally stealthy attacks are defined as those attacks for which the estimate of the local coupling is not different from what it would be in nominal conditions. And this is guaranteed by the design of delta DIL hat. On the other hand, globally stealthy attacks are those attacks that are both locally stealthy and the effect that they have on the state of each subsystem lies within the kernel of the coupling matrices of all the other subsystems. This is a quite frequent condition that we find in distributed cyber attack diagnosis schemes, and it basically means that an attack is constrained to be only local if it wants to maintain stealthiness at a global level. Okay, so having presented our scheme, let me present a simulation example. We have a setup in which we have a large-scale system with 4 subsystems. All the subsystems have homogeneous dynamics. And we consider the first subsystem to be subject to attack. The attack injects an input bias, which is the blue line in the top figure, as well as a compensating bias on the communication to the supervisory level in order to maintain local stealthiness. This has a clear effect on tracking, as we can see from the blue dashed line, which the controller should be tracking the origin, and instead it's not tracking the origin. Our results show that local stealthy attacks can still be detected by the supervisory level. And here we make use of this metric IF in order to show what proportion of intersection the 2 sets DS and DL have. Okay, so in this paper, we have presented hierarchical attack detection, where different trusted information was exploited for diagnosis. This scheme relies on limited information exchange between different levels, such as the convergence rate and the parameters of the reduced unknown input observer. And as future work, we want to consider both more realistic modeling schemes, how to do isolation of attack subsystems, and reconfiguration control strategies. So how to react to the knowledge that an attack is present on the system. And with this, I would like to thank you, and please feel free to reach out if you have any comments or questions.